Okay, so good morning. So the other day we have started the basics of cryptography and we have introduced the classical ciphers, right? Then we have stopped at the point of introducing to the modern ciphers. And then the other day Professor Aishwarya has given about the fundamentals, backgrounds of various crypto systems and all. So now we continue our discussion. So what we have learned in the previous classes were about that the classical ciphers are of actually based on what are the categories, like we said, what are the categories we said? Number one, based on the keys, right? You have what types? You have symmetric, and then you have asymmetric, then we have keyless, right? So this is one classification we saw. The other classification, what is that? The way the text is organized. What is the way the text is organized? You have block and you have stream, right? And what is the third one? The operation, the technique. So operation or technique, right? So we saw two types. One is the substitution and the permutation. We saw various ciphers. All the classical ciphers what we saw, either they are block based or stream based. Similarly, they follow either substitution or permutation, right? But when we have concluded the previous session, we said these are all classical ciphers. Like, what is our focus? Our focus is on the modern ciphers, right? So all the modern ciphers, what we are actually dealing with, all the modern ciphers, they follow what? They follow both block and stream. They also follow the substitution operation and permutation operation. You can't rely only on the one operation. By the way, what is the goal of substitution, we said? What is the goal of the cryptographers by performing the substitution operations? To confuse the attacker, right? The goal of performing the permutation operation is to diffuse the information, right? So we proceed our interaction. We have actually the stream ciphers we discussed the block ciphers. Now in future we will be discussing in combinations. Now if you look at closely, the way the stream ciphers have worked is this way. So you take the stream of plain text alphabets. So the stream of plain text alphabets. So your P is the plain text, P1, P2, P3, so on is the stream of alphabets. Then you have the key alphabets. K1, K2, K3, so on. All these key alphabets, and you have the plain alphabets, they produce your cipher alphabets, right? Cipher alphabets. So you have the encryption algorithm performing the operation to produce the cipher alphabets. Now we saw certain ciphers. Additive ciphers. Additive ciphers are, you have seen additive ciphers which are actually like a Caesar cipher. They comes under the category of what? The stream ciphers, right? What you did, you took every plain alphabet and then substituted with a alphabet that with which it is mapped, right? So it's a stream cipher, right? Not only the additive ciphers, other monoalphabetic ciphers that whatever we discussed, they are also stream ciphers because they follow one-to-one relation and it's the stream ciphers. Similarly, Vigneri cipher. which is having the binary table in the background, it is also a stream cipher, right? Then we actually, saw the block ciphers, wherein which what we did, if you look at the block ciphers operation, you have a plain text. Then what you do that plain text? You take the plain text, then what you do the next? So divide. Before that, before encryption, what you do is, so you have to take the plain text, divide into blocks, equal length blocks. So the example that what you are seeing, what is the length of the block? What is the length of the block? You see the length of the block is 3 alphabets. How many blocks are there? 3 blocks are there. So what you do is that you take the key, apply the key over every block and produce the ciphertext for that particular block. So take an example, PLA. So you get the ciphertext for that particular block. Similarly, INT, get the ciphertext for that particular block, right? We will see there are different modes of operations of this block on the blocks that we will see later. But now, for you to understand is that you take the plain text block, apply the encryption algorithm and the key, you get the ciphertext block, right? So what are the block ciphers we have already discussed? Your Playfair, where in which you saw with the Playfair matrix, right? Have you remembered or you forgot, by the way, right? So Playfair matrix you saw, so where in which the block size is 2, right? And then we saw Hill ciphers, right? Hill ciphers are also block ciphers, right? Then, by the way, you just note down this cipher, okay? In 1939, Alexander D. Akpeyev, in his book by the name Codes and Ciphers, he gave this particular challenge, okay? What is the challenge? He asked the reader, find out what is the plain text. Of course, you need not write the plain text. You can just Google it with the title Alexander D. Akpeyev challenge. Okay. You see, interestingly, different people have tried to solve this particular challenge in a different ways. Okay. Still, people could not identify what is this cipher, right? So please have a look at this. And by the way, when you are looking at, you should see how different people have approached this problem in a different ways. Okay. How different people have approached this particular problem, because you have the ciphertext, how to do the cryptanalysis, because you have only the ciphertext, right? You have only the ciphertext, and it appears that you have the ciphertext which is of the blocks sizes, each block of size say 5. Is it so? So please check once the solutions that are there, and every solution has narrated their own logic. So please check it once. Then we proceed with the modern ciphers. The other day I said, for the modern ciphers, you have, in terms of keys, you have symmetric ciphers and asymmetric ciphers, right? So what the symmetric ciphers do? So you have Alice and you have Bob, right? So Alice wants to send a message to Bob, okay? So C is equal to E of the plain text P comma K. So C is sent. So this is your communication channel and C is sent, and Bob would do the decryption. P is equal to D of C comma K, and K should be there at the both receiver and as well as the both at sender and as well as the receiver sides. So this is the symmetric scenario, right? The same is given here. So you see the modern block ciphers which are symmetric in nature, they encrypt what? An n-bit block of plain text, because divide the plain text into blocks, block size is of length n bit, and obviously you decrypt at the receiver side n bit block of ciphertext. So that means what happen is your plain text, this particular P is divided into blocks B1, B2, B3, so on. When you apply the encryption, what you get is the cipher blocks C1, C2, C3, so on, and at the receiver you decrypt the blocks to get back your plain blocks P1. So you decrypt it and you get the plain text, where in which the plain text is nothing but your B1, B2, so on, right? So every block gets decrypted and you get the plain text back at the receiver side, right? So the point is that you should have the common key between the both sides. Now the point is, I need to divide my plain text, right? I need to divide my plain text, this is P, into the blocks, right? This is my plain text, okay? My plain text I wanted to divide into blocks. Are the blocks are of equal length, or blocks are of variable length? Blocks are of equal length, right? Now how do I divide my plain text in a way that to get the equal length blocks? So imagine that I want my plain block size to be of 64 bit, okay? So this is 64 bit block, this is 64 bit, and so on. Okay, in this case, I can see that 1, 2, 3, 4, 5. So I could 5 into 64 bit. 5 blocks, each is of 64. Is it that my plain text would be of that much length always? No. So what I should do? How do I get equal length blocks? So the typical operation that we need to do is that you take the plain text and see whether I get equal length blocks or not. If I don't get, what is that I should do is, imagine I could make the first 4 blocks are of 64 bit. Imagine my last block is I'm not getting 64 bits in the plain text. Okay, so what I should do is I should perform certain padding here. I should perform certain padding here. By the way, is it that padding is something new? Is it that we have not discussed in the previous sessions? One time pad is one thing. Okay, any other answer? The padding. Okay, you remember, when we were doing one particular matrix, when we are arranging the plain text in the form of a matrix, our entire matrix cells were not getting filled. We have filled the rest of the blank cells with the filler characters. X, Y, Z, some filler characters we have done. Do you remember that? The same kind of an operation that we need to do. I'm not saying that you have take some filler characters and fill it. There is a process here to perform the padding, but typically padding is that you need to fill that particular gap so that even the last block is also of 64 bit. So you need to perform the padding. That's what that means, So if the message is fewer than n bits, either fewer than n bits or some integer multiple of n bits. See, imagine if my message is of length 5 into 64, how many blocks I can make? 5 blocks. Imagine if my message length is of integer multiple, say take an example, some 8 into 64. How many blocks I can make is 8. But is it that my message would be always some integer multiple of length of the block? Certainly not. So obviously your last block would be of not length equal to the n. So I make the padding, right? Now, so if you take any ciphers, modern ciphers, typically the block size examples. So these are all various block sizes. Okay, 64-bit block, 128-bit block, 256-bit block, 512 block. These are all the message blocks in different encryption algorithms of the modern ciphers. Okay, so I just skip this. So you see this problem. Suppose that we have a block cipher where the block size is 64. If there are 10 ones in the ciphertext, how many trial and error test does Eve need to do recover the plain text from the intercepted ciphertext, provided the cipher is a substitution cipher, the cipher is transposition cipher. Please note down this problem. You have a block cipher. Okay. You have a block cipher. The block size is of 64-bit. Okay. And if you notice the ciphertext, there are 10 ones in the ciphertext. There are 10 ones in the ciphertext. Now the point is, if the attacker needs to recover the plain text, is it that the entire ciphertext is given? Is it that entire ciphertext is given? It says there are 10 ones in the ciphertext. That means what? That means what? The rest are all? Is it that the 10 ones positions are given? Then the attackers need to recover the plain text from this scenario. Now the point is, how many brute force attempts that would be required? Imagine if this cipher is from a substitution cipher or if it is from a permutation cipher. Think on this. Any answers? How many bits are there in the ciphertext? Your plain text block is 64, so your ciphertext is also 64. Now, you don't know which operation is done, substitution or permutation. If it is substitution, how many brute force attempts are needed? If you have 10 ones and the rest are all 0. Similarly, if you have transposition cipher, how many brute force operations are needed? So how do you do that? Any answers, by the way? 64? 64C? 10 for substitution cipher. Okay. What about transposition? Sorry? 2 power 64. Okay. When you say 2 power 64, why? Okay. What happens in the case of transposition? Plain text? Okay. So keep this point in mind. We will discuss the solution later. So now we will proceed with the modern ciphers. Now the question what actually we posed here will give you an understanding about when I want to see the security strength of the substitution cipher comparing with the security strength of the transposition cipher, which is more secure. Okay, the substitution ciphers are more secure than transposition ciphers, but we need both because we have two goals to achieve. Okay, so this question gives you an understanding about what is the strength of substitution ciphers and what is the strength of transposition ciphers. We will discuss the solution later. Now, the other day also concluded with the components needed for modern ciphers, because in the modern ciphers what we are doing is performing the substitution and permutation. The substitution and permutation, right? In order to do these two things, modern ciphers depends on certain boxes called S box, as well as the permutation operation we call it as P box. Okay. Modern ciphers depend on two types of boxes called S box and P box. Okay. So this S box indicate which bits should be substituted for what bit. Okay. And remember, this is fixed. If you take any cipher, the S boxes are already fixed. Similarly, the P box indicates permutation positions of bits. Okay. So the S box indicates which bit should be substituted for what bit. The P box indicates permutation positions of the bits. There are actually the different types of P boxes. One is straight, the other one is compression, the other one is expansion. Okay, the other one is expansion. So look at the types of P boxes. What do you understand from the first box? This is a straight P box. What it says? Yes, it's 1 to 1, but the point if you look at, the first bit should go to the fourth location. The second bit should go to the first bit location. Third bit should go to the fifth bit location. The fourth bit should go to the third location, and fifth one goes to the second location. So 1 to 1. This is called straight P box. So it is telling permutation of the positions of the bits. Right? What next you have? You have compression. So the box takes how many bits as input? 5. How many bits is it producing? 3. So that means it is compressing. You notice that the first bit is going to the first bit. You compress the second one. Third one goes to the second. Fourth gets compressed in this case. Fifth goes to the third. So compression. Right? Next, the expansion. Observe the expansion box. What happened? You see, you have only 3 bits as inputs, you have 5 bits as outputs. So how do you get extra 2 bits? From where they are coming? Are they coming from somewhere else? No, they are coming from the given input source. What is the input source? Is 1, 2, 3. So you see here, 1 is anyway 1, it is also going as the 4th bit. Similarly, 2 is going as the 5th bit, 3 is as 2nd bit as well as the 3rd bit. So in that way, what is that we have got from the given 3 bits, we have expanded to 5 bits by repeating the given bits itself. So whenever you wanted to expand, it's not that you will pick from somewhere, but comes from within the given input. Okay. But if you notice, this is perfectly invertible one. It is perfectly invertible. What about compression and expansion? Can you invert them? So if you look at the given example here, this is the example of a straight P box. You see here, if you notice the box, there are certain numbers. What are these numbers? These numbers indicate the bit positions. So you have imagined 1 to 64. When that 1 to 64 undergoes this box, what would be the first bit of the output? The given input 58th bit, the given input 58th bit would be the first bit. Given input 50th bit is the second bit. That's how the permutation positions gets adjusted as per this particular straight P box. Okay. If you look at the compression box, it is with n inputs and m outputs, where your output bits are less than the inputs. That's what we have checked. Okay. Similarly, you have an expansion box wherein which you have n inputs and m outputs. Now the number of outputs is more. Okay. So finally, to conclude this, your P box is invertible, especially the straight P box, but compression and expansion P boxes are not invertible. What is the question that comes now? What is the question that comes now? What is the question? How the sender and receiver will have? So I frame the question this way, whatever he is asking. When we use encryption and decryption, the decryption is supposed to be reversible. When we perform an operation and we say that that operation is not invertible, how do we do? at the decryption. Are you able to follow? We say we need reversible operations, and we say that these boxes are not invertible. If I apply compression operation or compression P box or expansion P box, how do I do at the decryption side? Question is there, right? So the question, right? So again, the same examples. These are all not invertible. So how do we do it? Then we said for substitution operation, what is the box we have? S box. Okay. So an X box is typically an M cross N box. Okay. Like you saw the permutation box, right? P box, which has certain numbers indicating which bit has to go where. Similarly, S box is also can be regarded or can be viewed as an M cross N matrix. Okay. Look at this particular table. So this is my box. This is my box. I call it as S box. Okay. If you see this S box, it has rows and it has columns. Okay. It has rows, it has columns. So row 0, 1, 0, 0, 0, 1, 1, 0, 1, 1 columns. Okay. This is a kind of, an S box. If you see here, imagine I have an input. Say, take an example, my input is, say, 1, 0, 1. My input is 1, 0, 1. I need to find a string. Bit string. By sending this 101 to this particular S box, I need to find a substitution string. Are you able to follow? If it is permutation, what you do? If it is simple permutation, what you do? You can swap the bit positions, right? As per the P box or whatever it is. Now, if you notice this, your leftmost bit is what? 1. Your rightmost is like, the remaining bits are 0, 1. Your leftmost one indicates which row you should pick. What is the rows? You have 0, 1. So the leftmost bit is 1. So which row I should pick? The second row. Right? And what are the remaining bits? 0, 1. Right? What is the 0, 1 column? What is the corresponding value? So what is that I am doing? I am going to take 101 as my input, and this gets substituted with what bit string? This gets substituted with what string? 0, 0. So there is and remember, this particular substitution box is fixed. In the sense, this is the box given and you take any 3 bits, those 3 bits can be substituted with the bits that are given here. How do you substitute? By following the logic in the sense, take the leftmost bit that gives you which one? Row or column? Row. Remaining 2 bits indicate the column you should pick, and in this case, this one. This is how you need to get what are the bits that are to be substituted. Okay. This is one example. It's not that you have only this particular S box which is fixed. This is one particular example, right? So in this case, again, you see here, what about 0, 1, 0? So 0, 1, 0 produces output 0, 1. Okay. In terms of invertibility, S box is what? May or may not be invertible. S box may be invertible, may not be invertible. In an invertible S box, the number of input bits should be the same as the number of output bits, because it is right. Now tell me, the S box what we saw is an invertible or non-invertible? You are giving 101 as an input and getting 101 are essentially like 3 bits, and you are getting 2 bits. So it's a non-invertible one, right? Similar to your P box, you have a straightforward P box which is invertible, compression and expansion which are not invertible, right? There are other examples of S box. Look at the left side one. Invertible or non-invertible? This one. Because you are giving 3 bits as input, how many bits you are getting output? 3. Right. So we go directly to the modern ciphers. So these are the blocks, primitives that are behind these this one, the modern ciphers. Okay. What we are going to now talk is now modern block ciphers. Modern block ciphers. Again, our focus, I said modern block ciphers follow both operations. What are the operations? And one parameter is, I have not written. What was that other one? Modern block ciphers deal with substitution and permutation. What is that? Symmetric or asymmetric. So our focus is modern block ciphers which are symmetric. Okay. We deal now the modern block ciphers which are symmetric. So we deal now with the modern block ciphers which are symmetric. Okay. The roots for modern block ciphers which are symmetric lies with the ciphers. The most popular ones are the Fiestel ciphers. The Fiestel ciphers. Okay. So the majority of the symmetric block ciphers are of the category called Fiestel ciphers. Why they are called as Fiestel ciphers, we will discuss it later. We will discuss. So before we proceed, you need to understand one thing. I am implementing a cryptographic solution for my security problem. I said statement, I am implementing a cryptographic solution for my security problem. Then so far whatever we discussed, based on that, what you may think, oh, that cryptographic solution you said, either it could be symmetric or asymmetric. That's what you will think. That could be either, based on substitution or permutation operations, block or stream, like that. Then I said, no, all modern ciphers are all following substitution and permutations. So that means you think, okay, your solution could be either symmetric or asymmetric, and obviously following both substitution and permutation operations, right? But is the thought process? Substantially not, in the sense that when I say I have a cryptographic solution for my security problem, I'll write here a cryptographic solution for a given security problem will not just have only symmetric, will not have just only asymmetric, okay, but what will have, it will need the cryptographic algorithms for key exchange, it will need algorithms for securing the confidentiality, it needs algorithms for ensuring the integrity and also authentication. So that means my cryptographic solution deal with confidentiality of communication, deal with key exchange, deal with authentication. Then only I can say that I am providing a cryptographic solution. Okay? I cannot simply say that I am implementing symmetric key algorithm and I am providing a cryptographic solution. We've discussed a couple of security objectives. We said you need confidentiality, you need integrity, you need authentication, you need non-authorization, non-repudiation and all that, right? So, if you observe, I wanted to ensure confidentiality. How I do it? I will go for only symmetric encryption techniques. I will go for symmetric encryption techniques, right? Now, what is the challenge with symmetric encryption techniques? What is the challenge that with symmetric encryption techniques? What is the challenge? How both Bob and Alice have the same key, right? So for that purpose, I need to have key exchange. Which key exchange? The symmetric key has to be exchanged. For that purpose, I go for asymmetric cryptography. For that purpose, I go for asymmetric cryptography. Okay? Then, what is the other dimension? What is the other dimension? To understand who is the sender, who is the receiver, whether this is the message that the sender has sent. In order to do that, it's called authentication, and for that purpose, we need to go for keyless ciphers. Then only I can say I am providing a cryptographic solution. Okay. So these are the typical examples. If you see here, AES is Advanced Encryption Standard, which is a symmetric cipher used to secure the data or provide the confidentiality. Now, when I implement AES, what I should do on top of AES? I need to exchange the common key, and for that purpose, I may go for Diffie-Hellman key exchange algorithm. By the way, have you checked that paper? Today morning I have shared in the WhatsApp. In 1978, the paper was written by Diffie-Hellman. You notice what is this point says? The Diffie-Hellman is a cryptographic primitive used to exchange the keys. Which keys? Symmetric keys. Then you have a hashing algorithm called secure hash algorithm SHA, which is used for authentication and integrity purposes, right? Then one more important point. In modern ciphers, in all modern ciphers, we said, we are following block-based ciphers. Typically, there are two types of keys. Okay. In all modern ciphers, you have two types of keys. So, all modern ciphers two types of keys. Are we dealing with asymmetric ciphers here? Are we dealing here with asymmetric ciphers? We are dealing with symmetric ciphers. But what is the statement given? There are two types of keys. That doesn't mean that we are talking about asymmetric. We are talking about symmetric only. Okay. But have you noticed in that communication between Alice and Bob, two keys or one key? Did you see one key or two keys? Only one key, right? So, C is equal to E of P comma K, P is equal to D of C comma K. There is only one key. But what is the statement says? There are two keys. Okay. What are the two keys? In all modern ciphers of block, symmetric ciphers, we use two types of keys. Number one, what is that meaning here is, the K what we have written here is the encryption key. The key that what we have talked here is the main key, right? The main key. So, the user provides, the sender provides, while encrypting, only one key, that is K. Okay. But from the given K, encryption process, I say encryption process generates subkeys, or you call them as round keys. Okay, because all modern ciphers, Playfair cipher or whatever the ciphers we discussed, when you take the one plain text block, you perform encryption, you got the ciphertext, right? Again you repeated it. Again the encryption process repeated it on the same ciphertext. I repeat the question. Playfair cipher we saw. You took the plain text block. What is the size of block? What is the size of block? Playfair 2. Perform the encryption based on the 3 steps of logic. You got the ciphertext. Have you done this encryption process again on the ciphertext? What did we do with the affine? Affine. You did first multiplicative, then what you did? Take the ciphertext, perform again what? Additive cipher. So 2 times you have done. Okay. Have you noticed a double transposition? Double transposition. Do you remember double transposition? Permutation cipher. What we did there? Took the plain text, transposed based on the given key, take the ciphertext, then what you did? Again transposed it, double transposition, right? So that means so far whatever we discussed, you could notice that it is not that we are restricting ourselves by performing encryption only one time, rather we repeat. So when you repeat, what happens? It is like this. Number 1, just plain text to ciphertext. Otherwise, what is the second approach of affine cipher? Plain text and key 1, get the ciphertext 1, then take ciphertext 1, apply key 2, get the cipher. You remember? This is affine, right? What is the other one? Double transposition, plain text, key, get cipher, again apply cipher with the same key, get, this is transposition we have done. You remember double transposition? You could recall it or not? The other day we discussed, right? So that means we are repeating the encryption process. Now coming back to this current discussion about the, 2 keys. Number 1, I am giving only 1 key, but from that I am producing subkeys. Why I am producing subkeys? The reason is simple. So what I do is, I take the plain text P, I take the key K, okay, and I have to perform encryption. This encryption, I will not just do only once, I repeat it, okay. So I do encryption, say 10 times or 10 rounds, okay, say 10 rounds. That means what? I take my plain text P, apply K, E to get the ciphertext. But now what I do is that, since I am performing 10 times or 10 rounds, what I do? I take my plain text and I take my key, but from this particular key, what I do is I generate 10 keys, K1, K2, so on, K10. And these 10 keys, I submit them to my encryption process. So C1 is equal to E of P comma K1, then C2 is equal to E of C1 comma K2, and so on. I take C10 E of C9 comma K10. This my C10 is the ciphertext of P. Okay. So my encryption process has undergone how many rounds? 10 rounds. Every round, what I did? I gave a key. Is it that I gave the same key K? No. From K, I generated 10 different keys, right? I generated 10 different keys from the given key. This generating 10 different keys happens through key generation algorithm or key expansion algorithm. Are you able to follow? This is what is the happens under all modern ciphers. All modern ciphers, whether you learn any modern cipher, what is the one component in that algorithm? Number one, encryption process. Number two, key generation or expansion process. Why do you discuss about that key generation or expansion process? Because your encryption is happening for certain number of rounds, and every round needs a key, which we call it as a round key or sub key. This K1, K2, so on, K10, they are called sub keys or round keys. They are called sub keys or round keys, and they need to be produced from the given key. That's what is discussed here. So all block ciphers, there are of two types of keys. The first is the cipher key, the second is the round key. The cipher key is the random string of bits. Okay. What we are talking here is that particular K. Right? And remember, it is supposed to be random. But is it truly random? No. All the system generated numbers are not truly random numbers, but they are all pseudo random numbers. Right? So all modern block ciphers have a separate algorithm called key schedule algorithm, key generation algorithm, or key expansion algorithm. Because from the given key, you need to produce subkeys. So what is the purpose? The purpose of using this key expansion, key schedule algorithm is to generate for each round slightly different key than the previous key. So that means, if you notice, K1 is not equal to K2. Similarly, is not equal to K3 and so on. So each one is unique. Okay. Now, sir, the question is what? What is the question that can come here? What is the question that comes here? What is the question that can come here? Single point of failure, okay, on this particular context. Sir, the question is this: when I implement symmetric, I am also implementing asymmetric for the purpose of key exchange. Which key exchange? K. Now you said what? There are round keys. There are round keys. Is it that I need to exchange round keys also? Is it that receiver should get round keys also? Is it that the sender has to exchange round keys also? Why? Because you need not worry about exchanging the round keys. The reason is, sender exchange the main key K, receiver again generates what? Round keys. Receiver generates round keys. Receiver need not worry about generating, about the round keys. The algorithm can be followed. Okay. Algorithm is pseudo random. Which algorithm is pseudo random? Which algorithm is pseudo random or random? Key generation. Key generation algorithm is random. What is this? The key is supposed to be random. Which key? The key, K. Is it subkeys generation random? No. Because you have key generation algorithm is there, right? When there is an algorithm, can it be random? Key schedule algorithm, right? Since what is this is the generation of K is random, and from K getting K1 to K10 is through key generation, key schedule, right? But why do it this way? Why do it with this way? Just encrypt, send it. Why to do repeat it? Why to repeat it? Right? 10 times, 5 times, 16 times. Why to repeat? And in order to repeat it, you need generating the keys. Are you able to follow? Why to do this way? So think on this third question. What are the two questions I asked? I said two questions. Already I gave two questions. This is the third one. Right? Why to do this way? Now, so all modern ciphers, their backbone is the Fiestel network. Their backbone is called Fiestel network. All, not all, it's a majority of the modern symmetric block ciphers. AES is not a Fiestel one, but there are so many popular commercially deployed modern block ciphers. These are all Fiestel networks. They are called Fiestel. The German inventor or cryptographer by name Fiestel has produced a network or an architecture which is called a Fiestel network architecture, and the diagram shows the simple one. Are we talking about block or stream? Block. So I have a block of plain text. I have a block of plain text. What Fiestel said is, take the plain text block, divide into two halves. So imagine if it is 64-bit block, then what happens? This is 32-bit left half, 32-bit right half. Okay? And he said, look, divide into two halves, keep the left one half as it is. Keep one half as it is. Pick the second half, apply the function, transformation function on it. Apply transformation function on it, which typically you can think it as an encryption process. Okay. What function it is varies from algorithm to algorithm. but skeleton structure is this. Apply the function, output of that function, combine that with the second half. What is that? Output of the transformation function, combine that with the second half. So in this case, you have two halves, left and right. Picked the right one, applied the transformation function. Output is combined with left half. Okay. So whatever that output, that goes as the new right. The old right forms the new left. Is that clear? You took the block, divided into two halves, kept the one block as it is, picked the right one block, the other block, applied the transformation function, output is combined with the leftover block. After combining, when I say combining, it is nothing but your bitwise XOR operation. Okay, bitwise XOR operation. So combine it, that produces a new input to the right side one. The earlier right is the new left. This is the structure. And he says, you iterate this process. Means what? Again, keep this left as it is, take the right, apply. Apply what? Transformation function. Iterate this. Okay. You can iterate for 10 times, 16 times. How many number of times you want, you can iterate. Okay. So this is the the Fiestel network. So as I said, split the data into two parts, apply the transformation function on one of the part, and which transformation varies from different to different algorithms. Output of that function is XORed with the other half. Right. Now, I said this is the transformation function. Also can be called as round function. Also it is called as round function. Right. Now, though it is not given here, when I say this is the f is the round function, it is taking the input from the right half. So my f is round function. What is the input to that f? Input to this f is your r. Do you think r alone would come? What else can come? Key. Because you have generated k1, k2, k3, so on, right? What are all they? They are round keys. So though it is not explicitly given here, what actually you will be getting is the round key ki. Right. So this is the backbone of the majority of the modern ciphers. Now repeat this number of times, 5 times, 10 times. There are certain tests that are conducted. Typically, if you repeat for 5 times, it is sufficient. But the standard algorithms, they like DES, it repeats for say 16 times. Okay. So if you notice, the Fiestel function is the basis for several algorithms, including DES, Blowfish, Twofish, RC5, Mars, T, so on. Okay. There are so many algorithms which are block symmetric ciphers, which are based on Fiestel network. So the main difference between these functions is about exact nature of the round function. So that means if you understand the skeleton structure of Fiestel and understand one of these algorithms, understanding the rest of the algorithms is easy, because what else actually you are actually doing in the other algorithm is how actually is what happening in this particular round function f, what is happening in the round function f, and number of iterations that you are performing. And most probably the key scheduling algorithm, because what is needed? What is needed for the encryption process? You need the round key. So that is the one which varies. Okay. So next we start the most prominent modern block cipher, which is the DES. Now tell me, so we are going to discuss data encryption standard. Fundamentally, what type of algorithm it is? Symmetric. Then block. Then both substitution and permutation. And what else? What else? Yes, it is based on Fiestel structure. It is based on the Fiestel structure. Okay. Data encryption standard. It is symmetric in nature, block cipher, substitution, permutations, and Fiestel structure. In such case, what is the next point we discuss? What is the next point we discuss? Size of the block. Key size. Then then what else we discuss? What else? What else? Correct. These are all the points. See, we need to discuss. What else? On top of this? Correct. And before that? How do you do substitution? Right? These are the things we need to discuss. That would be there in the whole the discussion aspect of. So the DES is a complex combination of what it says. What it says? It is both substitution and permutation. And what it says? You perform these substitution and transposition operations in the form of a round function how many times? 16 times. Right? And then, what is the size of the block? 64 bits. So, your plain text block size is 64. What is the length of the key that you give? 64-bit length key. How many subkeys are needed? How many subkeys are needed? Yeah, how many? 16 subkeys are needed because you have 16 rounds, right? So, what is this diagram says? What is the Fiestel first operation, Fiestel network? Divide into left and right. Once you divide left and right, keep one half as it is, then take the other one, apply the transformation function. Now, if you notice, what DES follow is, divides into two halves your plain text block as left and right. So, left is kept as it is, you take the right. So, this is what? Why? It is 32-bit. 64, right? Your plain text block is of size 64-bit, divided into two halves, so 32 and 32. And you need to combine the key. Which key it is? Round key. Right? When you say combine, what is the typical operation we said? Bitwise XOR. Output of that undergoes substitution operation, right? What do you need for this purpose? Output of that undergoes a permutation operation. For this you need then this output is combined with what? The left. What do you mean by combine? With to produce new right, and the old right is the new left. That means you start, what do you start? Next round, right? So now tell me, what is the round function here? The whole aspect is regarded as round function, right? Are you able to follow? So same thing. The plain text is taken, which is of length 64. Now, what is that length given for key? What is the length given for key? What we said? What is this here? Yes. 8 bits are out from the given 64 bits. Then, what is the final output of the DES algorithm? What would be the length? So that means you apply the DES on the plain text block, you divide into multiple blocks, each block undergoes the DES, produces the cipher for that particular block, right? So there are encryption algorithm steps. Number 1, the plain text undergoes initially a transformation operation through initial permutation operation. That is the first step of the algorithm. First step of the algorithm is to permute the given input of 64-bit length. For that purpose, what is needed? You require a P box. But we don't call formally here as a P box, we call it as IP box, because your first step is performing a permutation and you call it as initial permutation, right? The rest proceeds. And remember, since we have done a permutation operation in the very beginning, after completing the number of rounds, which are 16, at the end, the final output also undergoes a reverse process called inverse permutation. So, you did a permutation in the very beginning, after 16 rounds, you perform the reverse permutation to that, which is through again what? Using P box. Now, we call that P box as IP inverse box. The reason is you did a P operation in the beginning and you are doing an inverse P operation now. There it is IP box, this is IP inverse box. This is the final step. Okay. But anyway, we will come to that later, but you need to understand that. Now, this is the encryption. There are about 4 steps. How do we do that is a different ballgame. Overall there are 4 steps. This is on the plain text side. What is on the happening on the key side? Why do we need a key processing algorithm? Because why do we need here? We need to generate round keys. So you need a key processing algorithm to generate round keys. So if you notice the steps involved in the round key generation process, the initial 64-bit key is mapped to 56-bit. Then the 56-bit text or the key text undergoes a permutation operation, and obviously you need P box for this, separate P box. Then for each round you need to generate or produce a subkey. There are 16 rounds. How do you do that? Through the operations such as a left circular shift and permutation. What is meant by left circular shift? So shift in this way to the bit position to the left, to the bit position to the left, to the bit position to the left, and it is circular. We will discuss that later. So, okay, this is how you perform the shift operations and at a circular shift operations. This is to produce what? Not random, round keys. What is random? The key that you have already got, the 64-bit key, is a random one. So this is the overall structure of DES algorithm. So the algorithm takes, you can see, I am discussing all this from William Stallings. So I think the book is already shared with you. So this is the plain text block, and this is the cipher key. What is the length of cipher key? 64-bit key is given, but on the key side, if you notice, it undergoes a permutation operation to get you 56-bit. And from then onwards, you generate round keys. By the way, what is the size of round key? 48-bit. Each round key of size 48-bit. On the plain text side, what you did? Take the plain text, perform the initial permutation, then enters the round. Round 1, round 2, so on, round 16. Every round produce the text of size 64, because your block size is of 64. So finally, after 16th round, you perform a 32-bit swap operation. What is meant by 32-bit swap operation? Whatever the round 16 output, the right half of 32-bit comes as the left one goes as the right. That is the swap. Then after doing it, you have done the inverse initial permutation, which produces the 64-bit cipher text of your 64-bit plain text. Now this is for one block. Now that means, imagine your plain text is of length of some size, and for that you got some 10 blocks. Then what you do? You have to do this for each of these blocks. One advantage is that since each execution gives you the ciphertext of that block, you can simultaneously do the operation on all blocks at a time. Right? You submit, take all 10 blocks, take that same key. Okay. The given cipher key goes for all blocks. For each block, the key will not get changed. Whatever is the number of blocks of your plain text, your capital K given is same. What varies? The round key is varying. Are you able to follow? So, shall we take a break, and we'll come in detail this one. In detail, what is happening in the algorithm we will discuss. So now, so far this is the overview of the DES. Then we see what happens in each round. What happens in each round we will discuss. Now when you understand the DES, understanding remaining modern block ciphers which are of Fiestel backbone is easy. The reason is, what varies? The inside round function varies and your key scheduling process. Rest, dividing into two halves, performing the operations and all would be the same. Okay.